Now that we discussed eigenvalues, our next order of business is to figure out how to find eigenvalues. And for this, let's find the eigenvalues of 1652. And let me give you a little bit of motivation for the formula that we'll use. So remember the eigenvalue equation, AV equals lambda V, and we want to find this lambda. If you put everything on the left-hand side, you get AV minus lambda V equals 0. And then we can factor out the V. But before that, notice, since we want to write this in terms of matrices, lambda V is the same thing as lambda IV equals 0, where, if you want, I is what's called the identity matrix. 1, 0, 0, 1, which has the property that if you apply I to itself, it just gives itself. And now we can properly factor out V. So we get A minus lambda I V equals 0. This is the 0 vector. And then there's a fact in linear algebra that says as follows. If there is a non-zero vector V that solves this equation, then this matrix here is what's called not invertible, and therefore its determinant is 0. So I did cover a whole month of linear algebra in this sentence. So if you haven't taken it and feel overwhelmed, it's completely normal. But in the end, we then get determinant of A minus lambda I equals 0. And that is our eigenvalue equation. And this we want to use to solve for lambda. But by the way, there's a nice mnemonic about this. Because A minus lambda I, it looks a bit like Ali. So ALI. So sometimes I might say Muhammad Ali. Or Muhammad. Right. All right. And now let's do this. So here we'll kind of do the slow way. And then in the next example, we'll do a slightly faster way. So here, determinant of A minus lambda I, that is the determinant of our matrix 1, 6, 5, 2 minus lambda times identity matrix 1, 0, 0, 1. And that becomes the determinant. Again, if you put everything together, it's 1 minus lambda times 1. So 1 minus lambda, 6 minus lambda times 0, so 6, 5 minus lambda times 0, 5, and then 2 minus lambda. And then that's just the determinant of 1 minus lambda, 6, 5, 2 minus lambda. And I like to remind you, the determinant of A, B, C, D, we did this with var of par, is AD minus BC. So this becomes 1 minus lambda times 2 minus lambda minus 6 times 5. And then you expand this out. So 2 minus lambda minus 2 lambda plus lambda squared minus 30. And then we get lambda squared minus 3 lambda minus 28. And now think, you want the product to be minus 28, but the sum to be minus 3. Like minus 7 and 4 works. And remember, so that was the determinant. And our equation says we need to set this equal to 0. So we set this equal to 0, and then our eigenvalues in the end become lambda equals 7 and lambda equals -4. And if it's the first time that you see this, you might be like, holy moly, but don't worry, because we will literally do the exact same procedure 10 more times at least. So it's another one of those things. It looks scary at the beginning, but then you'll see it's always the same thing. And again, to recap, what did we do? We took determinant of a minus lambda I. We simplified this, took the definition of a determinant, and set everything equal to 0. And now to motivate the fast way, notice what we really did. The matrix was 1, 6, 5, 2, and really all we did was subtract lambda from the diagonals. So in fact, let's do the same thing, but faster. So let's do the same, but with A is 0, 6, minus 1, 5. So once again, let's do determinant of A minus lambda I. So again, just subtract lambda from the diagonals. So it becomes 0 minus lambda. So minus lambda. And then 6 minus 0 minus 1. And then 5 minus lambda. So again, subtract lambda from the diagonal. And then you just use a definition of the determinant. So minus lambda, 5 minus lambda, minus 6 times minus 1. And so minus 5 lambda plus lambda squared plus 6. Beware of the sign mistakes. Number one mistakes that people do here. So minus 6 times minus 1 is plus 6. So we have lambda squared minus 5 lambda plus 6, which you can factor out as lambda minus 2 times lambda minus 3. That's the determinant. You set it equal to 0, and you get lambda equals 2 or lambda equals 3. And that's the fast way, and that's all she wrote. So we found eigenvalues now. Next order of business in the next video is to find the eigenvectors.